Good afternoon, everyone. Welcome back. And we're very excited to have Tengyu for this session. And Tengyu Ma is an assistant professor at Stanford. Sorry, I didn't check. At Stanford, who's done some really amazing work on understanding theoretically a lot of the modern machine learning technologies, including language models. And I guess is also doing some Bay Area adventures recently. And I was fortunate to work with Tengyu when I was a grad student at Stanford. And I'm very excited to hear his talk on understanding in context learning.
Should I use that?
This one. You have a mic.
Oh, okay, yeah. Sounds great. Yeah. Thanks so much for the introduction. Yeah, thanks for having me here. Yeah, it's a great pleasure to be here again. So I'm going to talk about in-context learning. So this is a phenomenon in large language model these days that people found very interesting. I think I only have like 30 slides, so feel free to interrupt me at any point. I'm allocated 1 hour and a half, but I guess it's going to be more like 1 hour at most. So so in-context learning, I think what's the in-context learning? This is one thing that people found very special to large autoregressive language models. In some sense, the definition is that the large language model can learn to solve a new task simply by reading a prompt containing just concatenation of a few input and output pairs. So sometimes people call it few-shot settings because you only have a few input-output pairs. But the real thing is that you put all of these input-output pairs in the prompt without any parameter updates. So you don't have to change the parameters in the large language model. And this makes a big difference in some sense because I think this new wave of AI in some sense is enabled by this without parameter update part, because this makes it much easier to deploy a large language model in a new environment. Before, you have to go through all of these steps on collecting data, fine-tuning or training from scratch, and doing test, train, test, split. And now, none of those, right? You just you can do anything just with only a prompt, and the prompt can contain a few input-output pairs, and you can learn a new task very quickly. So just give you some examples. This is what I did, last night or 2 nights ago. So I guess the resolution is not great, but this is I'm using the GPT playground. So basically, you can have 2 examples. Albert Einstein was German, and Gandhi was Indian. And then you can just write Marie Curie and then you leave a blank. And then you let the model to generate the next token. And the next token generated will be next few tokens will be Polish French, and note that I think note that here there is some learning here, because it's not trivial to know that if you don't have these 2 examples, you don't know what we should fill in here. It may be kind of like nationality. It could be also like a occupation, like in this case, right? So if you have the 2 examples, which is about occupation, then you can find out that she's a physicist and chemist. So there's some learning here for sure, because at least you are learning what the task is supposed to be. There are other cases, for example, where you can label the sentiment of a sentence by doing this, right? You first give 3 examples where you first have the sentence and then you say it's positive, and you have the sentence and you say this is negative, and then at the end you ask a question. You have a new sentence, and then you let the model to generate, and then it generates positive. So you solve the problem by, and also the format is exactly right, because you just output the exactly right format, and this actually makes it very easy because you can detect the answer. So basically now you can solve sentiment analysis by just using in-context learning without doing any training of the model. But the exact format here can be anything, right? As long as you have any kind of like reasonable format here, and it will follow the format in most of the cases. So I see. So this is a little bit more kind of mathematical cases where you have a Q&A, and you can see like here I'm using this bracket. I guess most of the people probably can guess what the bracket means. In this case, like this, I'm trying to kind of like really find a case where you have to learn something. So if you look at the examples, the exemplars, you can probably guess the bracket means sum, because I face all the 4 examples. And then for the last example, you ask this question, and then the model will complete the prompt or generate next token, which is going to be 9. So that's a successful case. So this is in-context learning, or sometimes people call it few-shot learning as well. But I think there's something wrong with my animation. Sorry. Okay. So Of course, don't take it for granted, because it's not always the case. There's some finesse you need to do here. For example, if you use ChatGPT 4.0 latest, which is probably like the August 12th version, and then if you just do the exact same thing, I was using GPT 3.5 before, and if you do the exact same thing, you're gonna have this as the output, which doesn't follow the format. And you can try to fix it by saying like, please complete a prompt with as few words as possible. Then it will just follow the format that you wanted. So it's not like just completely trivial. And one of the reasons for this to happen is that I think these days people use a lot of, like OpenAI use a lot of RLHF here, so that the models are incentivized to give longer and more comprehensive and more friendly answers, as opposed to this kind of like very concise answers. So it's not like it's not always the case. It does depend on how you train the model, so on and so forth. This is another case, which is a little bit similar. So here you can see there's some conflict between the examples I gave and the priors the model has. Right, the model has the prior that parenthesis means something, right? It means the parenthesis, and then when you have these examples, it says that, okay, actually you are not formatting the expressions very well. So actually, I was kind of like a little worried, because I heard of these kind of issues that the RHF will destroy some of the in-context learning, and when I was preparing this, I couldn't kind of like some of these early things. It took some time for me to reproduce them, because I have to choose the 3.5. I have to go to the OpenAI playground and choose the 3.5, and it was a little. Like for like 5 minutes, I was worried that I couldn't produce even a single example, and and this is some of the failure trials I had during that journey. And this is another case that the failures is a bit different, which is here I even kind of like I forget about the format. So so this is a case where you have 1 minus 3 and 4, 3 minus 5 and 8, so on and so forth. And I give the prompt to help them a little bit guess what the symbol minus mean, and answer the last question. So I guess most of us can see that the minus actually means plus, but actually, to my surprise, to my I'm not extremely surprised, but still to my surprise, the models couldn't guess that the minus is the sum. It actually tries to give you some other pattern matching. It says that maybe this corresponds to taking the absolute value of the absolute difference of the two numbers and followed by adding a certain value. And it tries to see what values it wants to add to make the formula right. And it says, okay, you need to add 2 here, you need to add 2 here, and add 6 and 4 here. So it didn't find a consistent pattern, but still try to make some prediction. And eventually it decides to add 5 or something. I don't know. Anyway, so the models are still not that great, especially when they have a conflict with the prior knowledge. So it's not entirely trivial. Yeah, and this is a case where it's actually working, but it's not kind of following the format. It's almost the same case, but I'm using GPT-4 latest. So it gets the parenthesis means plus. That's correct, but somehow the format is not followed in the right way. So all of this is just saying that it's not like entirely trivial, and it does depend on how you train the model, so on and so forth. And there are some possible mechanisms. I think I'm trying to do a kind of like a taxonomy or some kind of like a categorization of 2 different type of learnings you can think of here. And this is originally discussed in this paper, very nice paper about what in-context learning is actually how it's working. So you can probably say that there are probably 2 type of learning here. One learning is that you are following the format. So basically, in this case, where you have positive and negative labels, in some sense, to solve this problem, you don't have to learn. You don't have to learn from the new examples sentiment analysis. You just have to learn that this is a task of sentiment analysis. So the models already know how to solve sentiment analysis, and the only thing that the models needs to learn is to learn what is the label set. It's positive and negative. It's not 1 and 0, right? And how do you output a label? You should just output a label as text without saying anything else. So in some sense, in this case, you can argue that it only needs to learn to give the answer after the A. Sorry. Oh, I'm using a different example where there's no A. But you need to learn the answer to give the answer after the sentence, and also you need to know the label set, which is negative and positive as strings. And another case is that you have to learn.
So how robust are some of these things? So like instead of labeling it with the examples of positive, negative, and then it's a lot easier to think about positive and negative as being associated with sentiment analysis. But if I label it with other things like A and B, does it still work?
Yeah, it should work at least largely. I think there are a lot of studies about this.
But it's actually solving sentiment analysis for this, or
Yes. So if you label them with different labels, it still works to some degree. I'll have something at the very end of the slides about how much the degradation the performance is if you change the label set. But at least by and large, for the purpose right now, like they still work to some degree. Yeah. Yeah, and you sometimes can flip the labels. Like if you flip labels, it still works up to some. Like you can still learn the negative relation there as well. So and this is the case where the second case I would argue is that you are learning the fundamental relationship in some sense, but not just only the label set. So because you are learning some kind of new relationship in some sense. Of course, because here, like you have to understand the data, right? It's not like you are just learning the labels is digits, but you are learning the relationship that the parenthesis actually means the summation. Yeah, I'm sorry that the text is a little bit small, so I'm not sure whether you can everyone see this? Anyway, I'm already done with this slide. Anyway, okay, so basically, how do we have some theoretical explanations for in-context learning? I think what's the question? The question here is that the models are only trained to predict next token on some data, right? And so why these models are only trained on this can follow the format and also can learn some input-output relationship without even any parameter update. So that's the main question. And I think the methodology most of the people are taking is that we make some kind of like very simplifying assumptions. At least these are what my papers are taking as a methodology, and many people are doing the same thing. So you make some simplifying assumptions on the pre-training data sets. So you don't have to kind of care about the pre-training data sets. It depends on how you train it, right? If you train it with Gaussian data IID, you wouldn't learn any signal, right? So and then you make some assumptions on the pre-training process. For example, you assume that you can minimize the pre-training loss exactly, maybe on the empirical data, on the population data, and with respect to some kind of like architecture, like within some kind of like architectural choice. And then you say, we proved that the models can do some in-context learning on some still relatively simple downstream tasks. That's the methodology, nothing surprising. So I guess I'll show a few examples of this kind of like analysis that tries to kind of tries to answer the question to some degree. So this is one of the paper I wrote with some of my former students, Michael and also Aditi and Percy Liang. So we try to expand this. So basically, we try to understand why there's a learning capability, right, without any parameter updates. We are trying to say this is the model is doing some implicit Bayesian inference. So maybe let me just walk through the setup. So we have the pre-trained data is generally like the following. Yeah, go ahead.
So you're saying it's learning a concept.
Yep.
What if it's sort of doing pattern matching and saying, look, among it's seen a lot of patterns like this, and the closest thing probably is replacing the parentheses with the plus, and it would match that data. And you could imagine somebody doing this even if they had no idea what plus means.
Yeah. So I think let me try to see how do I. So I'm tempted to say the following. So learning and pattern matching are the same, anyways, for me. Like like.
Retrieval. Like, is it like has it like already learned some function and is it just retrieving one of those functions? Like, is that correct? Is like
But
What
maybe
asking is maybe the following. So if you had the same kind of example, but the next thing you asked it was some much larger, sum of two integers which are much larger.
Yep.
So that it had never seen them before. Would it still?
Much larger, maybe not, but at least you can be out of domain to some degree. It doesn't have to be exactly like the examples you gave are probably one digit some problems, but you can extrapolate to probably 2 digits, for example. And maybe just go back to the naming a little bit, just even though that could be confusing. So for machine learners, just to clarify, for machine learners, learning and pattern matching are not fundamentally different, at least until a certain time. Like if you look at one of the books that I think there was a machine learning book called Machine Learning and Pattern Matching, Bishops, yes, exactly. So pattern matching is a form of learning. It's just probably not the strongest form of learning you can think of. So and the retrieval, could be considered as a form of learning, right? Like k nearest neighbors is a form of learning. So at least if you use the old-fashioned machine learning kind of like languages, these are all kind of some form of learning. Yeah. But what you said is still very possible. I don't have an answer to exactly the hypothesis you had, right? So it's quite possible that the models know already know a certain set of rules, right? They knows how to do summation, it knows how to do minus, and then they just try to find out which of the existing rules they know how to do matches the exemplars. But I would say that's also a form of learning to some degree. Because think about how do you do the standard machine learning, right? So you do VC like pack learning, right? So it's kind of like you have a set of hypotheses, and you are trying to try whether each of the hypotheses matches your examples, and whatever matches the examples, then that's the hypothesis you output, right? You have five hypotheses: summation, abstraction, and OR, and you try all of them on your exemplars, and you output the one, right? And whether you understand that as a at the end, you probably didn't, right? You just find pattern. It's a pattern matching.
Beyond the choice of language for this, these seem like very different tasks. In one case, if it's single digit or even double digit, this thing has a lot of data, and it will find the pair 2 and 7 or the pair 83 and 12 somewhere, and we'll see what their sum is. As opposed to it's actually mapping parentheses to a functionality and then applying that functionality. Those are very different.
I would say that's just a sample complexity issue, right? So if you have a lot of data, so first of all, none of this is overfitting, right? Because you didn't see 3 minus 6 before in the exemplars. But this prompt is this is literally what you are given to the model at this point.
But the model has been trained on a large model.
Yes, that's right. But that's the pre-training part. Here I'm talking about the learning after you are given the model. Let's say the model is not even the model is given to you as a black box, right? So it's like you have like for example you have a human who is doing this. If a human is given this, do you think it's a learning or not?
Okay. So if you're saying the model is a black box,
yeah.
I'm thinking of a daemon in there with a huge database which contains lots of such 1 plus 3 equal to 4, etc., etc. So the daemon's running around in there. Now there's a difference between two different models. One where the daemon understands what plus means and time means, times means, and so on. There's another one where the daemon only understands, what goes around, looks at these strings and says, look, if I run around, I found a string where it said 1, plus 3. Well, that seems pretty close to 1 parentheses 3 and then 4 and so on, and all these other things match up. So I'm going to take the next place where I find 3 parentheses 9 or 3 plus 9,
right.
3 plus 6, and then I've got 9. Okay, so if you had a student like this who was acting like this daemon, we say, okay, they managed to get not a 0 on the test.
Yep.
But maybe let's not give them any.
I agree. I'm just saying like I'm the only thing I'm saying. So I completely agree with you. I cannot tell apart which case it is, right? Whether it's just really doing pure pattern matching or doing some kind of more deep reasoning. I cannot really tell the difference of them. At least I don't think anybody can really answer this exactly either. But what I was trying to say is that at least in the old days, like 5 years ago, you wouldn't even attempt to distinguish these two types of learning. Like because, for example, pike learning, if you do pike learning, you run a pike learning algorithm, I don't think you can argue that it's doing any real reasoning. It's still pattern matching, right?
There is a difference here, which you
okay.
Listen, when you're doing, you have a hypothesis class, you are exactly learning the concept. So there's a difference here whether you're learning by virtue of the family of concepts having small complexity or your input space having small complexity. Right?
Oh, I think here the input space has big complexity.
Okay, but this is, so this is I think what I'm trying to understand.
Yep.
Question about.
Yep.
But if the input space is actually relatively small, then you can learn by memorization.
Yep.
Neighbors,
Yep. That's a great question. Yes.
People,
Yes.
Right? And that is somewhat distinct. I mean, it's difficult maybe to get a mathematical definition, but it is distinct concept and learning a function.
Yeah.
Whether you understand it or not, I don't understand what understand means. But like at least in terms of having concept. And so here, I think what you're saying is that it's possible that in this subtraction task, right, the space is actually small enough that maybe it is just like some kind of there are two levels here, right? The level of what the model is doing and the in-context level, right? So the model level, maybe it is actually just memorizing.
I think that's possible. It's very possible you are memorizing a few possible hypotheses, or maybe many hypotheses.
Memorizing the entire space, because this entire space here is only size 100.
Oh, I don't think that's the case, because you can test this with 2 digits, 3 digits, or 10 digits. Like
Yeah, so I mean, just to like push on the robustness angle for these kinds of things, right? So in one of those examples, the parentheses should be interpreted as plus, right? So now what happens if I do like 3 parentheses 8 parentheses 9?
Okay.
Is it actually going to generalize the understanding that this is in an abstract sense addition, or is it a smaller complexity of the space of inputs where it learns it, in sort of a 2 input kind of context, right?
I think if your format is too different from anything that is kind of like I think in your particular case probably wouldn't work. But some other format would work, where you can change this to maybe S. I tried it last night. Some letter, that's fine. You can change the maybe. Actually, if you use the dollar signs, it doesn't work because it's confused with the LaTeX. You can see from the output. So.
I think we're also touching on like issues about how I write my exams. When I write exams for students, is I teach them, the single parenthesis example, and the test is 2 parentheses, and that's.
I think 2 parentheses might be fine, but but too many is probably gonna 3. If you just 9 parentheses, nothing else. But for example, if you encode 3 by 3 parentheses, I think that wouldn't work. But if you just add 3 parentheses here as a symbol, that's probably fine. Yeah. But okay. But going back to Nati's question, so I think there's a I think there's a this is a I think I appreciate the distinction here. But one thing is whether you have a small hypothesis space. Another thing is whether you have let's talk about learning of the large language model, right? One option is that you have a small hypothesis space, summation, subtraction, maybe multiplication, right? Another possibility is you actually memorize the entire table of all the summations and subtractions of 2 digits, right? So I think the latter case sounds unlikely to me, just because you can test this with more digits. You can test this with multiple other questions. You can have like powers. You can have like also all of the other questions. Like most of the tests are not numerical, right? Like you have. So this one, how do you remember, right? How do you, this one, you can still remember in some sense, but generally, I do feel like there's no. The space that we have tested, the input space we have tested are very large. Like in general, like the community has tested. So it shouldn't be like they just completely memorize everything there. And also people have tried to flip the label and permute the label in some sense, and all of those still works. So those are not from the prior knowledge of the model. Maybe that's another thing, right? So what if you change the, I guess maybe here if you change the, so I do have some examples here. Later, wait, where is it? In this case, what if you change this to maybe like something like Simons, and this is Berkeley, and do you think that's a kind of a form of at least you rule out the possibility of memorizing the truth table, right? So what if this positive thing is? I'm pretty sure if you try this, if the positive is relabeled by Simons Institute and this is relabeled by Berkeley, I think. And Berkeley will mean neutral, and Simons Institute will mean positive. Sorry, no.
Yeah. Remember this issue as you go through
your remaining examples. Sure.
Maybe the answer itself.
Yeah, sounds good. Yeah. And also probably just no answers, anyways.
I'm curious if you can maybe completely avoid this issue of memorizing or learning a hypothesis. And can we instead just think of, when we just look at this in context test, did we actually gain anything by learning we did before? Is it possible to learn, like, I would say that if the in context test there's enough data there that I could actually just do it without any other knowledge that I learned during the training of the model, or if I actually, is it ambiguous if I don't have the full model and I needed the full model in order to figure out how to do it? Right then I could say I'm actually I learned something for the full model.
Yeah, so what if your task is a linear regression task? Do you think that's a...
I don't need the full model.
Sorry, what if the downstream...
But the sentiment analysis, they do. Right, so if you...
Yes. Yeah, so I don't have it on I don't have it on the slides, but in one of my papers we do try linear regression, just a very abstract linear regression problem. You have x and y, no just y is a function, linear function of x, and it's a synthetic, and it still works to some degree. Not great, but at least.
Actually, you don't need any. I need to talk about that later.
Okay, sure. Okay, sounds good. Okay, let me continue. Yeah. Thanks. But this is but so far I'm trying to just okay. But anyway, regardless of all the discussions we had about what's called learning or not, just for the sake of like this talk, for the rest of the, let's just think of learning as you can solve this task. That's it. How no matter how you solve it, as long as you can solve a new task, that's called learning. Yeah, sounds good. Thanks. Okay, so and where the learning come from? So this is one way to explain where the learning come from. So you consider this data distribution where your traditional data distribution is a family of documents. Document is the unit you are training on. A document is an example, and you can imagine that you are generating the document by the following. You first have a family or distribution of hidden Markov models. That's called script H. Is a distribution of hidden Markov models. And for each document, you first pick a hidden Markov model, and then you generate the tokens, each of the tokens following the hidden Markov model. You first choose an initial state, and then you keep running the hidden Markov model to generate a sequence. So that's so it's kind of a mixture model. You are doing a mixture of hidden Markov model. But it's an infinite mixture of many hidden Markov models. And you assume that you are minimizing the next token prediction loss to the base optimal. So you say you have an almighty architecture, like a model family, so that you can do whatever you want, and you minimize the population risk so that you get the base optimal for this. So and then if you think about this, right, the best way to predict next token is to actually just run Bayesian inference. So how do you predict, given some kind of prefix, how do you predict next token? The best, theoretically best way is to do the following. You give a prefix, you first infer which age it comes from. You cannot really exactly infer exactly. You do the compute posterior of the age, and then you use the inferred age or the posterior of age as well as the prefix to generate next token. So basically, you say condition on the age I inferred, and technically actually you draw example from the posterior, and then use that age as the condition to generate, and also the prefix, and you generate next token given the hidden Markov model. So basically, you use the inferred age to do the next word prediction problem when you predict next word. So okay, so that's the and I'm claiming that this is kind of like a form of learning because you are learning implicitly which age it comes from. You are learning the pattern because in some sense the hidden Markov model is a way to insist some coherent pattern in the sequence because the whole sequence is generated by a whole single hidden Markov model. So that's why there's a coherent pattern along the sequence. And how do you follow that pattern is by you infer the posterior age. So if you infer the posterior age, you are you learn the pattern in some sense, and then use the pattern to solve the downstream task. So that's and this is a trivial statement because it's the same as the Bayesian inference. Like every time you have such a problem, this is the optimal thing to do. So so basically, I'm claiming that the learning capabilities stem from the structure in the data because the data are from a hidden Markov model where you have a hidden variable model. You have some kind of like a hidden. Here, the hidden variable is the hidden variable is the HMM itself, but not the hidden variables in the HMM. The HMM is the hidden variable. So every document has this internal consistency enabled by the hidden variable. And then if a model fits the data, it needs to have the implicit capability of learning the hidden variable. And that's where the learning come from. So just because you fit the data, you have to be consistent with the pattern, and that's why you learn the pattern in some sense. And in the context of that paper, so this is almost a trivial statement in some sense. The surprising thing here is that there's still some train test differences, right? The training data is a continuous stream of tokens from the HMM, right? You just keep generating tokens from the same HMM. That's how the document is generated. But when you have a test, you are having this in-context learning case where you have multiple exemplars. So the way we formalize that, which is pretty natural in this context is that you are basically running HMM with a reset, right? This is one example, and then you reset. You say, I'm going to do another independent example. I reset my hidden variable, the hidden state in the HMM, and I generate another example, and then I reset and generate another example, so on and so forth. So, can I say it?
The document contains the vertical bars? Like
No. The document doesn't have the vertical bars. That part is actually easy to deal with in most cases, but that's just the vertical bars is for my visualization. Yeah. So basically, but these are independent. So it's not a continuous stream of sequences from the same HMM. It's from the same HMM, but with a reset in the HMM. So basically, and also, if this is already mixed, then there's nothing interesting here. So you probably have to assume that this is not mixed enough, and then you reset, and then it's not mixed enough, and so on and so forth.
Just checking. So it's the same HMM for each of these examples, but it's unknown to the model. So it's sampled from the prior or HMMs.
Yes, it's unknown to the model because the model are only given these tokens, right? So basically, at the test time, the model needs to infer which HMM it come from. If there's no this resetting, then the test time is the same as train time, and then what you should do is to infer the HMM and then just keep generating, and so that you can solve your test task. But here, the challenge here is that in a test time, the data you got are not exactly the same as the data you got from the training because of the reset. Yeah. So and in our paper, the reset is just modeled by you resetting the hidden state of the HMM. It's modeling different exemplars, right? Because this is like a 3 + 6 is 9, and this is like 4 + 5 is again 9. But like each part is one exemplar in the in-context learning. So and because all the exemplars are independent, but in the training, it's like every document is a single stream. There's no independent structure there, right? Everything is correlated with each other. But in the test time, every exemplars are independent with each other, conditioned on the HMM. Okay.
Have you conducted experiments on synthetic data generated this way?
Yeah, we have done that. Yeah, and you can see it's very similar phenomenon. Yeah.
The training data is continuous, that it's not broken up in different ways. I mean.
Oh, that's my assumption. Like each document is kind of a continuous stream of, this is a modeling assumption that the training data seems to be more like a continuous stream of like that's the interesting part, right? If the training data is also like a QA, then there's no train test split. It's kind of less interesting in some sense. So what we're trying to answer is that even though the trainings are just documents from the web, every document is kind of like a continuous stream of like a tokens. But in a test, you can still have this individual exemplars one by one. I want to explain why this difference is not a big issue.
I'm guessing that this argument applies to any next token prediction model.
There's no transform. Yeah, we assume the model is almighty in the sense that you can express anything you want, and you assume you have infinite data in the pre-training and so on and so forth.
What is this K, the length of the training document and the number of states? Like, how should I think of it? Like, are the length of each training document roughly K? Is it much?
Yeah. So the length of the training document is much bigger than K. K is the length of the examples. Yeah. So the number of hidden state is a constant, I think. So K is not big enough to mix within that K example, the K tokens. But basically, if you don't have the reset, you assume this is going to be long enough to mix. But with each of the examples, you are not long enough to mix. At the end of the day, actually, if you look at the proofs, this is just some perturbation analysis. You just try to find out that how much negative impact the reset will make to your system, so that the reset doesn't really hurt you enough, so that you can still infer the hidden Markov model that is underlying. It's just like we don't want to cheat. If you just say with only one example you can infer, that's too much cheating. We just cheat a bit less in some sense. It's not like a very a lot of assumptions got involved, and eventually it's not a very clean analysis, I have to say. So I don't really recommend the proof. Recommend to read the proof. So but this is some conceptual kind of like thinking here mostly. Yeah. Okay, I'll continue. Okay, so okay, this is so basically we have this proof that where you can say that even despite some of these differences, under certain assumptions that control the differences, and you can prove that you can still learn. You can still infer the hidden variable with this this sequence, and then with the after you learn the hidden variable, which is the hidden Markov model that generates this sequence, you can naturally, like the model will just complete the solve the prompt. Yep. Yep.
So in your examples, you have replaced plus with a
Yes.
So are you assuming that the training data and this test data came from the same hidden Markov model or different ones?
Yeah, that's a great question. So so I think that's one of the okay, okay, maybe let me answer the question first, and then I say what's the limitation. So in the training data, you have a lot of hidden Markov models, like because each time you use a different hidden Markov model, and the test time you use another one. So in some sense, in that sense, if you okay, depending on what's the assumptions you make, right? If you assume that in the training examples you have 1 million documents, then you have seen 1 million hidden Markov model in the training, and then in a test you have the 1 million plus 1 hidden Markov model. But I think the theory in this paper doesn't really work that way. It assumes that you have population loss. You have minimized the population loss for the training. So in some sense, you have seen all the hidden Markov model already in the training, so that the test one is only one special hidden Markov model you are seeing. So which is actual limitation of this. I think that's what I'm saying next. So the limitation is that so it's unclear what, at least in the phrasing of the paper, it's unclear whether there's non-trivial generalization, right? Whether you have to see all the hidden Markov models in the training. So it's a little bit unclear just because we are the statement is written in a way that you are minimizing the population loss. It didn't really explicitly saying that you have to see all the hidden Markov models, but it's almost kind of the same. Anyway, so that's one problem. So basically the way to solve this problem is that if you can bound how many pre-training samples you see, then you can bound how many hidden Markov models you have seen. And then you can say that because I only have seen like 1 million of them, and then in a test I'm going to see a new one because everything is drawn randomly. So then that's okay.
Sorry, and your result wouldn't work if you said you saw all the hidden Markov models except this particular one, so that your loss is almost the same for all the rest. And so even then it doesn't work. The theory.
At least as written, at least the paper doesn't have a situation. I think you can make it work, but it's not going to be, yeah. Let's say it doesn't work. Let's just say it doesn't work. Yeah. So that's the limitation. Yeah. At least we don't know how to make it work in a clean way. So, yeah. And there's any questions? Okay. So, and another thing is that and also in some sense you shouldn't just believe that this can just happen out of the box without any additional restrictions, because the generalization requires some capacity constraints. Right, you need the models to be small enough so that because otherwise the model can do whatever they want on the pre-training samples. They just have to memorize the pre-training samples, and there's no generalization. So that's why I think in some sense this is the same question as this one. You have to introduce the architecture in some way so that this can work.
I'm wondering what would happen if two edge and in your training data set are contradicting to each other. So let's say one example is 3 plus 6 and 9.
That's not a problem because in the test time you see enough long sequence so that you can possibly infer which one it is. Right. So that's fine. Yeah. Okay. So this is a simplified data distribution. I think I have some sites in some other paper, but this is a paper by Percy and Greg Valiant's group. They propose this even simpler situation. So here there's no twin test differences actually, but but you have the generalization perspective, like whether you have seen all the possible hidden Markov models. But also this hidden Markov model is actually much easier. It's not actually written in a way that called the hidden Markov model. So basically, let me just go through this. So this is a linear regression data set where each training document is how do you generate a training document? You first generate a linear predictor from Gaussian, basically a vector theta, and then you sample a bunch of examples xi from Gaussian, just to make it simple. And then a document is a concatenation of all of the x and y's for n of them. for n plus 1 of them. Like so basically you can think of this as a data set with n plus 1 examples, but you concatenate them into a string. So that's the document, and where y is basically a linear function of xi plus noise. Technically this is still a hidden Markov model without, we don't even need a hidden state because you just keep generating more or less like independently, except that y depends on x, and that's the only dependencies between this between the tokens in this document. So from now on, I'm going to work with this example. So of course in the training task you are trying to predict yn plus 1 given all of the previous xi's and xn plus 1. So and you can see that intuitively the way to predict yn plus 1 given the prefix is that you probably should infer theta, and then and use theta times xn plus 1 to predict yn plus 1. That's kind of the learning you need to do if you want to solve this task. So and when you test exactly the same way. You just say I'm giving the prefix up to here, and then I ask the model to fill in the blank for the last one. And if you fill it, it means that you are learning the linear predictor theta in some sense. So and again, it's almost trivial in the sense that using the same argument. So if you have an almighty model which minimizes the loss on infinite documents, then it will perform Bayesian inference on a test document, which is actually a data set. I sometimes I use, it's a document, but actually it's also a data set because you have n training examples and one test example. So and because just following the same thing, right? The optimal thing for you to do to solve this task is you infer the theta first, and then you use the theta to compute yn plus 1. And for linear regression case, it happens that the Bayesian inference with all of this prior is the same as ridge regression, and the lambda, the regularized in the ridge regression corresponds to some of this covariance. Like there's some formula there which is pretty simple. Sorry, question. Okay, cool. So so this is basically I'm applying the same methodology for this simpler setup, and I get that you are doing ridge regression if you have almighty model that minimize the loss on the infinite documents. And now so now we can talk about a little bit more about whether you can introduce some more structures in the training and in the architecture. So that's where the transformer come into play. So you can say that so the question is that whether you can use a transformer to express the ridge regression learning algorithm in theory, right? So know that the transformer is supposed to take in this concatenation of x1, x2, x1, y1, x2, y2, so on and so forth, and then predict the yn plus 1. And what it needs to do implicitly is that you need to do this xx transpose plus I inverse, this kind of like you compute the covariance matrix, identity, and then take inverse and do some of kind of like formulas. So and it's not very hard to prove that you can actually use a transformer to solve this if you have n layers. So basically every layer is doing one step, incorporating one example. And the way to do it is that you try to basically, in some sense, the ridge regression estimate has this I plus xx transpose inverse thing, which is the hardest thing to approximate as a formula. So, and you approximate that by repeatedly applying this Sherman-Morrison formula, where each time you add one kind of like rank 1 component, because this is a sum of n components, n rank 1 components, and each time you incorporate one rank 1 components by using this formula, so that you can turn everything into a more kind of like the division here is a scalar, so this is easy, and then you can turn this into like a vector matrix product, something like that. And you can show that this can be done by attention, something like that. Nothing very, very hard, actually. I'm trying to abstract away the details just so that we don't get into the unnecessary details. But basically, you can say that transformers can implement a linear regression, ridge regression algorithm. Actually, transformers can do a lot of other things as well. It can approximate almost every Turing machine if you have some asterisks there. So it's not very surprising that ridge regression algorithm can be implemented by transformer. And empirically, you also know that if you only have very few layers, like here you need n layers, if you just do 2 or 3 layers, then transformers cannot learn a ridge regression algorithms empirically. It will learn something much simpler algorithms for learning the linear regression data set. And then the next result I'm going to show is that this is a theoretical result where you assume that the transformer just have one layer and it's linear attention without MLP. So it's very, very simplified one layer transformer without when the attention has a linear component. And then you can say that after such a restriction, then you can only learn one-step gradient descent learning algorithm. So basically, if you are just only learning the algorithm you are running for the linear regression data set is only just a simple gradient descent algorithm. And this is empirically actually true, like almost exactly if you run it, because theoretically it matches exactly for some coincidence in some sense. So this is the theory you can do. So basically, in the training time, as we said, you do a square loss and you predict 1 plus 1 given the x1 up to xn plus 1. And this f theta is a one-layer linear tension. I'm going to abstract away all the details there. So basically, for the way to think about one-layer linear tension is that the tension thing creates some quadratic thing, right? You are taking the inner product of the queries and the keys, and that's a quadratic thing. And then you multiply it with the value, which is a cubic. So basically, a tension will give you a cubic polynomial, and that's how. And in this case, basically you have a quadratic between xi and the yi's, and then you multiply by the xn plus 1, which is the value, which corresponds to the value function part. Which corresponds to the value part of the tension. So basically, you get a cubic polynomial of this kind of structure, and the thetas are the parameters in this cubic polynomial. Basically, this is your training loss. And when you test, and what's the optimal thing? The optimal thing you want to do is that if you don't have any restrictions, then the optimal predictor will be some linear predictor on top of xn plus 1, and this predictor is this Bayesian optimal thing where you do this ridge regression estimator. So, but this is something you cannot achieve because you don't have enough capacity to achieve this. The only capacity, the only functions you can represent is this kind of like a cubic functions. And basically, in some sense, the loss function is trying to say that you want to find the best predictor among this family that is as close to this as possible. And what is the best one among that family that is closest to the Bayesian optimal estimator? And here are some intuitions. I'm not going through the proof. So first of all, this is a cubic, right? So and this xn plus 1, there's nothing to discuss here because you always have to have xn plus 1. Eventually, you have a linear function on top of xn plus 1. So basically, it's only really about what this quadratic will be. And the quadratic is just you have the xij term and the yij term. And if you think about it, why you need xij when you do a prediction for when you solve linear regressions, right? It's not very useful. The regressions is really about knowing what's the correlation between x and y, but not the correlation between xi and xj, two examples. So that's why actually in the proof you'll see that at some point the xj term all got canceled out when you average over the data. So that's why the xi and xj term are not very useful. And xi-yj term is also not very useful because when you solve linear regression, you are trying to find out the correlation between xi and xj, but not xi and yj. Sorry, you are trying to solve the xi and yi, like the label and the input for the same example. You don't care about the correlation between input for the first example and the output of the second example. That's just not very useful for you. So that's why it doesn't really make much sense either. So basically, the only term that you are left with is xi and yi. So basically, this quadratic, the only thing that matters here is xi, yi. And also, you should treat all of the xi and yi's equally the same because there's no reason to prefer one example over the other. They're all symmetric. So basically, that means that eventually, the only predictor you can that makes sense among this family is just something like this: xi times yi, a summation, and then you take xn plus 1. And it turns out that this is the same as one-step gradient descent on this quadratic loss. So basically, this is if you do one step of gradient descent, basically you are getting xi times yi, which is the theta here you are using. And that's something we can prove formally, like exactly true. And this is oh gosh, I somehow wait, this is a very important references I didn't have. This has been done by 3 papers, including one paper from MIT group, from Silver groups, and one paper from my group, and one paper from Peter Bart's group. I think my paper is the weakest among the three of them, but this is the shared part of them. Somehow I'm missing that slides for all the references. My bad. Any questions? Okay. Sure. Yeah, of course.
I mean, the thing is here. Okay, I mean, there's the issue of representing it as a transformer, but in some sense, I claim that here, in all of these papers, you don't need any of these any of the learning. because the problem is there's enough, the sequence length is high enough that if you use just for something like so my gold standard is the shortest program learning rule, without any knowledge about what is linear regression, it'll actually succeed in predicting all of these things.
Yes, that's
so
right.
In some sense, you don't actually. It's not clear that you don't actually need all this. There's nothing here that you can convince me you're learning in the initial phase, right? Unlike with the HMMs, right?
But this is HMM, right? There's a hidden variable.
No, but like it's too easy of a setting, right? If there's a small class of H&Ms that's necessary to this small class is arbitrary. Okay, so here, maybe I'll give you an example here. What would convince me that if you would actually the linear predictor would always lie in a small subspace.
Okay.
The number of the context length was longer than the dimensionality of the small subspace, but smaller than the ambient dimensionality. Then you clearly are learning something. Because, but that's not the case here.
But you can make it work. I think
I know you can, but this is not the case here.
No. I think So like it's not the case here. Sure, I agree. But it's not the case here because the sparsity here doesn't work well with the transformer. So basically, there's two sample complexity here. One sample complexity is how many exemplars in the context you need to have. Another complexity is sample complexity is how many training documents you need.
And then here the outer sample complexity is 0.
Which sample complexity is?
Outer sample complexity. The number of documents you need, the number of outer documents you need is 0.
For this task?
Yes, which is exactly the problem.
Why? I didn't get it because
if you just have a single document,
yes,
the shortest program learning rule would be able to predict it perfectly.
But how do you know it's a linear regression problem or quadratic?
Because that is the shortest. The amount of data in the context here, the n is significantly larger than d. In all these examples, enough larger than d that would be the shortest program.
Shortest program among which family of programs?
It doesn't really matter too much. I mean, n is so much larger than d here, then it doesn't really matter.
Maybe you can take this, but I'm not sure I understand it. So because if you're only given one test document, which is a sequence of xi and yi's, you wouldn't know that this is a linear regression problem, right? Like you could overfit.
But the simplest explanation for predicting the y's from the x's is linear regression, right? Because the n here, I mean, these tests are, if you have d which is 5 and n which is 100, roughly what's numbers here, then that by itself is enough to figure out that it's linear regression. I don't need to know that it's linear regression.
Maybe how about let me say the following. So let me try to convince you in a slightly different way. So even in this setting, suppose you are in a setting that n for the number of exemplars in the context. If n is less than d, this still works.
If n is less than d?
Yeah, because if you believe in that you are learning the Bayesian optimal, if you believe that you are using ridge regression.
But this doesn't fit neither the theoretical explanation you gave us nor the empirical results in any of these three data.
No, the ridge regression does fit in empirical. I have a paper which shows that it's doing ridge regression. Oh yeah, I just didn't cite it somehow. Yeah, my bad about citation. I was trying to do the citation at the last round and I forgot about it. That's my thing. So, but the empirically, if you have enough layers, you are going to learn ridge regression, and the ridge regression will work even for n is less than d. At least it works to some degree, because that's the right. Like you have a double descent actually when you do in the context, and it exactly match the ridge regression very well. And if you don't have enough layers, you're going to match something closer to gradient descent or stochastic gradient descent.
I'm less familiar with, so I don't want to.
Yeah. I probably should have those kind of plots in the talk.
The important point here is it's important to really think about what is it you're actually learning in the outer, like what is the outer sample complexity? Like what is it you're actually learning in the outer thing? What is your class of possible things you're learning from? And what is the sample complexity? Because
the family of but that's the sample complexity. So basically there's a the inner sample complexity.
That's fine. That we understand.
But the outer sample complexity depends on the architecture that you choose. So basically, how do you prove outer sample complexity? Outer sample complexity means how many documents you need, right? So basically, that is just polynomial in the complexity of the transformers you are using. So basically, if you can prove expressivity, you can say that a small number of layers can express this learning algorithm. Then you can prove that your sample complexity for the documents is polynomial in the number of parameters in your transformer, or in the complexity of your transformer.
So that gives you an upper bound for your specific learning method. But if you're asking, you started this by saying, okay, I'm going to do something here, I'm going to learn something here. So I want to understand what is the sample complexity of your learning problem, and whether your method actually is efficient. Does it actually solve this learning problem in a reasonable sample complexity compared to the actual sample complexity of the learning problem? And here I'm claiming that you're right that your method has high sample complexity, but this is extremely inefficient because the sample complexity of the actual learning problem is 0.
I agree with everything else except the last sentence. The sample complexity of the actual problem is 0 because that depends on what assumptions you have. Maybe let's take it offline. I think we are almost there, but just yeah. But then maybe I'm saying the same thing a different way. So so the sample complexity is polynomial for constant number of layers of transformers. That's what we know. So basically, the results here by Bayes how it works is that you prove that the transformers can express the Bayesian optimal algorithm, or it can express the stochastic Whitney descent, whatever algorithms you want to learn. So basically, you say the transformers is capable of expressing those learning algorithms with constant number of layers, and then you prove that the so-called outer complexity, where the number of documents you need to learn these transformers is polynomial in the number of parameters of the transformer. So that's how you get a bound on the complexity of the number of documents. And some other works include, it also depends on the prior of the predictor. That matters if the prior is too kind of degraded, then it's kind of hard, and also whether it's sparse or not. And you can also analyze the tuning process on a two-layer transformer, which is pretty challenging. And also there are other works where you can say that, for example, you can say, here are some related works that transformers can implement, for example, SGD on a loss that involves learning with another small transformer. So transformers can be actually pretty expressive. You can actually run an SGD algorithm on another loss function that involves another transformer using a transformer. Anyway, so maybe another thing I forgot to mention here is that the results here also works for the case when y is nonlinear in xi. This is something I found very interesting. So basically, even the data you're given is not linear regression problem. It's just a nonlinear problem. As long as you have some certain symmetries, and you use a very weak transformer, then you still learn gradient descent on the quadratic loss with linear models. So basically, everything, the conclusion is exactly the same, even you replace y to be nonlinear of xi, as long as your transformers is weak. Anyway, okay, sounds good. So what time is it? So I guess I only actually have 2 slides here. So these are some empirical results to kind of like to validate some of the research, and it's also kind of actually there's also a new phenomenon here, which is about the size of the large language models. No, not a new, which is related to what we discussed, right? What all we're discussing is about whether the transformers is capable of expressing certain learning algorithm. If it's one layer, you can only express gradient descent, and if you have multiple layers, you can express the Bayesian optimal ridge regression. And here are some kind of like empirical data, which probably also anchors question a little bit. So this is kind of like what I was telling Anchor in the beginning. So you can try to have different, more challenging setups for the in-context learning. So the regular version is that you have negative and positive here, and the flip label case is that you just flip the 2 labels in your in-context exemplars. And there's also this so-called semantic unrelated targets, where you just label, change the positive to full and change negative to bar, or some random string. And in this case, you just need to follow the format, and then you need to just reuse the prior from the pre-training data. You know already some of the sentences are positive or negative implicitly, and you just have to figure out the format of the examples. But in these cases, you do have to learn the relationship. You have to learn here you are flipping the labels, and here you need to learn that full means positive and bar means negative. And here is some kind of like a clause that justifies that actually you are learning some brand new concept or relationships. So this is in a flip data case, and you can try different model size and here maybe just focus on this plot. So basically here you are flipping the label 100%. So all the labels got 100% flipped. But the evaluation is done by using the original label. So basically, if you are learning the flip label, then you should just be completely wrong. Like you get a 0% accuracy because your evaluation is using the original label, and but your exemplars are flipped. And that's what this model is doing. So this is not exactly 0%, but like 20%, which is kind of like 80% correct in some sense, and that's the largest model, Text Davinci 002. This is a paper like 1 year ago, and they require a lot of experiments here, so that's why they are using relatively small, older versions of the models. So basically, Text Davinci 002, I think, has probably like something like maybe on the order of like 100 billion parameters, and that's kind of like learning the flip labels. But for some of the smaller models, basically once you flip the labels, the performance becomes either still very high, which means that you didn't actually overwrite the labels. You are still using the original interpretation of the labels, or you are just write on a random performance. And the same thing happens on all the other charts where the larger models learn the flip labels because the performance drops, and the smaller models couldn't do that when the labels are flipped. So this is saying that actually the complexity of the transformer does matter. Like I think, to some degree, but I'm not saying like this is matters for the same reason exactly as the theory, because the theory is saying that the bigger the models is, you can express more complex learning algorithms. But here probably not necessarily exactly for the same reason. But at least the model complexity matters for the performance of learning the real, doing the real in context learning. And there are some theoretical explanations in some of the follow-up works here. So summary, I think the kind of the thesis is that the pre-training forces the models to be able to infer the hidden structure in the sequence, which is kind of a form of learning. And the optimal learning algorithm is the Bayesian estimator, where you estimate the best hidden structure, and then you use that to predict. But if you have limited expressivity, then you let the models to only implement suboptimal learning algorithm, which is probably what's kind of like happening right now. And some concluding thoughts, I guess this relates to a little bit to the pattern matching stuff. So I do think that current context learning is largely pattern matching. I think I would even be okay with removing largely. Just it sounds like just only pattern matching. Even linear regression, I would call it pattern matching in most cases. So maybe you can say pattern matching is a form of reasoning, but it's definitely not very kind of like a strong form of reasoning. And the reason why I brought up reasoning here is reasoning seems to be the main question right now for large language models going forward. So people believe that that's the at least I believe that that's the main thing that is missing here in OpenAI models, right? Like the reasoning, or any of the other models, like the big commercial models still don't have very good reasoning capability, and especially when you really involve some of the deductions, more deterministic deductions, right? So in some sense, it sounds to me that the models are good at doing some pattern matching, at least reasonable with doing some pattern matching, but not very good at very concrete deterministic deductions. And it sounds like this is a problem for the community. How do we have more reasoning capability? And what I was kind of like thinking about is that whether some of the research here for in-context learning for the would be helpful here. So can we? So basically, the whole thesis of the talk was that the loss functions and the data somehow encouraged the models to learn the patterns, to do the pattern matching. But if you change your goal, the goal is to learn some reasoning capability, then maybe you should engineer the data in some way so that the pre-training with some engineered data would encourage other kind of behaviors or phenomena for the downstream tasks, and the so-called other phenomena is the reasoning capability. But I don't have a good idea on how to do this. But that's just my concluding thoughts about open questions. Thanks very much.
Yeah, one of the questions I had is like in terms of how should we think about the learning an algorithm? Because even in the linear regression example, right, like if the theta and x were sampled from a very different distribution than the Gaussian, I don't think this would work, right? Like, so if it is very close, then probably it will, but if it's very far away, it wouldn't. So what does it mean to them to say that it has learned or it is implementing something like ridge regression? Because technically, if I had ridge it wouldn't matter what my x distribution of x and theta was.
Yeah.
But in this case, at least
Yeah, the way I'm thinking about it is that it's just all the generalization problem, right? So you learn the linear regression, you learn the ridge regression algorithm on the family of predictors, which is Gaussian, and whether you have all the generalization to other data sets or other predictors. And actually, we have done some experiments here in some of the other contexts of the some other papers, and there are some OOD generalization. It's not like that once you are not Gaussian at all, then it just doesn't work at all.
But like the distance, like I guess it's like how far away you are from that.
Yeah, so I think what's the truth is that the kind of what happens, I don't know how to explain it, but what happens is that for the distribution you have seen, for those kind of like linear predictors, the model is learning ridge regression, and for the if you go a little bit further away from the distribution, you are learning some other learning algorithm, which still makes some sense. It's a little bit weaker, but actually the learning algorithm is still okay. And then we are really, really far away, then just all bets are off. Sometimes it's because actually, but there are so many reasons why it doesn't work for when you extrapolate to infinity, because these are real numbers, right? When you're, for example, one trivial thing that we realized in our early research is that you can never have like a OOD extrapolation to infinity if you have the layer norm in it. Because the layer norm in the transformer will just kind of like normalize everything and make your output only constrained to a certain range, and there's no way you can have OOD extrapolation. So there are many other factors there if you talk about OOD extrapolation.
A very naive question. Suppose you provided you were doing sentiment analysis, but you gave only positive examples, and then your test is a negative one. What should the output should it output positive because everything else is positive?
Yeah, so I think what happens, I think I've actually tried this myself even. So if your labels are meaningful, are the right label, then the models will give you the right. I think I'm not entirely sure whether it will tell you exactly the word negative, but most likely it will tell you something like it'll do the task for you. Maybe not exactly following the same format because you haven't shown the format exactly, but it will work. And the reason is that you are using the semantical information from the pre-training, because you have pre-training on open web text also. So, but if your exemplars flip the labels, then I think it's going to be much difficult. Yeah, it's unclear what's going to happen. It also probably depends on the model size, as I said in the end, right? If it is a bigger model, maybe it learns how to flip the labels. If a smaller model, it just follows the prior information.
Two questions. One, so you're saying that in context when what happens is pattern matching, but I mean the sentiment analysis, for example, how is that? Do you consider that pattern matching, and how?
I think that might, if you use the labels that are consistent with the common sense, I would even say that that's not even pattern matching. That's just learning the format of the like you're just learning that the labels need to be called positive without a dot, without any other, right? You're just learning the label set. But if you're flipping the label, I would say that's pattern matching.
So can you learn? I mean, I'm curious. So many tests for the same set of inputs, and so they can have many different labels. Like for example,
yes.
The sentiment is positive or negative, or the answer to the question should be positive or negative.
Yes.
Whether it's a native English speaker or not.
Yep.
And so I think I didn't do this experiment that all of these would work with the.
If you give them the exemplars, yes.
If you give the example.
Yes. So the exemplars will tell you learn from the exemplars what's the task, right? Whether it's positive. And also you learn from the exemplars what are the label sets, how do you express your label.
So you're telling us that all these tasks are tasks that the system already knows about, and it just has to figure out which of this like finite set of tasks. I'm asking if this is what you're claiming, that the system kind of knows a finite set of tasks, and it's just doing pattern matchings of these tasks.
Maybe let me not give a direct answer for the first. So maybe let's think about how do I know? How do I answer a question? So you need experiments to ablate it, right? So that's the experiment we did. So basically, you are asking about this setting, and you don't know whether you are learning from the prior, like you don't know whether these outputs are done just by following the prior from the pre-training data set. So then what you do is you can flip the labels, or you can change the labels to something else, so that you force it to not use the prior. And if it still works, then you are learning the relationship. Otherwise, you are not learning the relationship. And you found out that actually the answer to this question, whether you are learning new relationship, depends on the model size. If it's a small model, then you are not learning you are only doing that. When you flip the labels, it doesn't learn. But if you have a big models, you learn you learn how to flip the labels, or use the different labels. That's the experiments here. So if you use a big model, when you test, your performance suddenly drops because that's your learning. You are testing on the original labels.
So does it mean that for the big models you are going beyond label match, beyond pattern matching?
It doesn't mean it's still pattern matching. Learning and pattern matching for me is the same. But it just you are not patching. You are not or maybe pattern matching.
Come on, on the last slide you said if you go to the last slide.
Yes. I think it's pattern matching. Yes. So I think the maximum is pattern matching, but there's something even weaker than pattern matching, which is you're learning a format. That's it. So pattern matching for me. And also maybe let's clarify what pattern matching means. Is it pattern matching to the existing pre-training data set, or pattern matching to the small number of exemplars in the context? By pattern matching, I mean you are doing pattern matching to the exemplars you are given. That's what I mean by pattern matching. You are matching the patterns in the exemplars.
But you are using some knowledge from before, right? Otherwise, how would you do addition to a new number? So there has to be some pattern matching to addition that was done in pre-training.
Yeah, but I think that's a different level in some sense. It's kind of like in some sense, I feel like you think about pack learning, right? So there are two things you have to know, two things you have to do, right? One thing is you have to define the hypothesis set. I think that's kind of like what you got from the pre-training, like you know the hypothesis set, and then which hypothesis is in the hypothesis set. That has to be decided on the fly when you see the number of exemplars, a few number of exemplars. Yeah.
So you consider that pattern matching?
I consider that as pattern matching. Even right? No, that's called pattern matching, right? You are selecting one hypothesis that matches the pattern of the exemplars. Anyway, okay, we can discuss that later. Okay. Okay.
Yeah, maybe while along that discussion, so the way people currently differentiate between retrieval and learning a task or pattern matching, whatever, by doing this reversal, you could imagine doing something different where, for example, we know that models get better at certain capabilities after fine tuning. We can see whether the model does improve at all compared to its pre-trained level within context learning. So in that case, you're actually qualitatively learning something more than just retrieving. Do you know if there's any evidence of something like that?
If you fine tune on the exemplars?
Yeah, but we know if we fine tune, we do improve
performance. Yes.
But do we also see something similar within context learning, where we go sort of beyond the pre-training capability because we've seen samples? So,
but I don't know how to compare, right? What's the baseline? What's the case that
Yeah, I guess you don't want to see saturation with number of samples or something like that.
But even you see saturations, it's still a form of learning. It's just a learning algorithm is not great. So for example, if you use k-nearest neighbors, you will see saturation.
Saturation after many more samples, I would consider that as in most of these cases, it saturates in 5 samples or something, right? So it feels like
maybe 30 or something. Yes, but saturation just could mean that you have a limited learning capability, but it doesn't necessarily mean that you are using the prior information or not, right? So. And another thing is that also the saturation is very hard to test because you go out of the context length, and also I also don't know what happens with the context. So even we are within context. You have a 1 million kind of context length, but it could be that when the context is longer than 2,000, it doesn't work actually. Even though it supports a longer context length, but actually implicitly it's not working very well. So it's very hard to delineate those kind of factors. Sure. Sure. Yeah.
So the other question is, there's a contrast here. So you described between the Bayesian. I think there's a contrast between the Bayesian estimation and being Bayesian and being doing out of sample generalization or reasoning or something like that. And I'm curious whether you think. How do you think this fits in here? In the sense that think of your Gaussian example, right? If all my thetas came from some distribution of thetas, then the Bayesian thing to do would be to stick, to always return something that's worth, even if actually I then have a test sample where the theta is very different.
That's what they actually do, right? So because you use the regularization to make the norm smaller.
But that's completely at odds with being good at these I guess you'd call that as not doing reasoning, or that you're completely at odds with being able to generalize out of distribution. Right? Because if I learn to do linear regression on one distribution, presumably I should be able to do it also when my theta come from a different distribution. But if I'm Bayesian, I'm not going to be able to do it.
I think there are two layers, right? When you are Bayesian, by being Bayesian, I just mean that you are implementing a ridge regression. You are if you exactly implement a ridge regression, then that's Bayesian.
Right? That's
Sorry, like just sorry. So like so when you say you implement a ridge regression, it also has two interpretations. One interpretation is you implement a ridge regression for the axis you have seen in the training set. Another thing is you implement a ridge regression for the axis x and y's that can be anything, like that can be OOD. So even when you declare that you are being Bayesian, and there are still kind of another OOD effect. Does it make sense? Maybe I'm complicating it.
You decide on source distribution. So you have a source distribution, it chooses theta, and it chooses x's, and then it gives me samples, and I'm being Bayesian, I'm doing the optimal thing for that source distribution.
Yes, which is a ridge regression.
If the theta comes from a spherical Gaussian, it's ridge regression.
Yes, exactly.
But if the theta comes from some other distribution, it's something else.
Yes, sure.
Okay.
That's right.
Suppose it actually comes from a shape distribution.
Yes.
Right? Not a spherical distribution. But now I see an example where the theta is from something that is just completely has the extremely low mass under this distribution. Right? So my thetas come from a distribution which is like has high variance in the first 10 coordinates and almost no no variance in the last 2 coordinates. Now I see something which is actually uses those 2 last 2 coordinates. What should I do? So the Bayesian thing would say, well, no, that's not in my distribution. I should never use those 2 coordinates.
Yes.
But what you would do, you personally, if I gave you this data, right, and you'd say, oh, all the training examples actually use the first 10 coordinates, but really here I have to use those 2 last coordinates because you're reasoning.
Yeah. So I think the experiment says that there is no such capability of this advanced reasoning you are talking about. I don't think the models have this capability. As long as you train the models on the synthetic data I defined, it wouldn't have such capability. It would just follow the prior. It would follow the Bayesian.
But we're somewhat, so that kind of suggests that you're saying, oh, the transformers are great. They're always doing the right thing, which is Bayesian. It's just that when we were explaining the reasoning, we're just explaining something unreasonable because we shouldn't be doing reasoning.
Because there is a gap between this and but that's the gap between the synthetic case and the real case. Because for the synthetic case, you are training on a very special data set, which is only a collection of documents which are sequence of x and y's. But when you are really doing the real thing, you have a much more diverse kind of data sets. So basically, I'm saying yes, you are right that if you are in this kind of linear regression setting, I don't think you should expect any real reasoning, right? Because the transformers are not total reason at all. So but if you are in the real world, you could possibly still expect to learn some reasoning some way, right? So and that's what we're trying to figure out. I don't know how to do it. I'm just saying that there's still a possibility, right? And I think that's kind of the hope. The hope seems to be that something like you have the weak to strong generalization in the sense that I'm sure you heard of this. I'm pretty obsessed with it, but I don't know how to do it. But the hope is that you train on weak data, which has very weak reasoning, but you can train a model that's such that after you see this weak reasoning data, and then you get a mathematician out of it who can solve Riemann hypothesis. I don't know, that's just only a question, but I'm not saying we have any ways to solve it.
So I have the question about the thing you mentioned earlier about the issue of the confounding between the context length of the model, the advertised marketing context length versus the actual context length, versus whether it can actually reason the 3 different things that are happening. You're saying it's hard to tell them apart. I'm just wondering, since you said that these things seem to be able to pick up formatting as the basic thing, wouldn't very verbose formatting of examples allow you to just, literally have something, booga, 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 something else, just spread it out and force it to kind of go across context? Wouldn't that answer the question of whether it's the context length versus
Oh, yeah. I'm not saying like it's impossible to tell apart. I'm just saying like you cannot do something like you need to do ablations to tell apart which part, to understand all different factors. Yeah. But I think what you said makes sense. Yeah.
You seem to argue that they're very good at capturing formatting and kind of learning what the format of the example.
Yeah. That's true.
So these are very interesting insight, but I'm trying to square this with I believe the Min et al. Paper in I thought they conducted ablations where you provide the formatting but random examples and you still got a boost
Yes.
in the performance downstream.
Yeah, because you learn the format.
But that sort of seems to and the drop from true examples to random examples, at least they claimed, was very small. I thought the entire argument was there is almost no in-context learning.
Yes.
How do you square that with
For those
actually explain in context?
For those kind of tasks, yes, you are just learning the format. As long as the format is right, you don't even need any relationship in the demonstration or exemplars. You just need the right demonstration of the format, but not the demonstration of the relationship in that paper's context. But that's for those kind of tasks, right? But for other tasks, you need,
Tasks were just classification, not right?
Yeah, but you can, for example, do a more challenging task, and then in that paper the performance is not great because the models are relatively small. So basically, there's some historical kind of things like during that time. I think the models don't have that good real, let's call it real in-context learning capability to get the input-output relationship, and that's why that paper is kind of like saying that, oh, actually in most of the cases we have tested on, you are just really only learning the format, but not any other learning of the relationship. But then later, I think when the models becomes better and bigger and bigger models and some of these a trillion of 500 billion parameter models, and they can actually gather some real input-output relationship. I think that's kind of like my maybe I'm not exactly, I'm not 100% sure, but I think that's my recollection. That's my reconstruction of the timeline in some sense.
So is there any published paper that discusses this, whether there's a robust refutation of the hypothesis saying you only get mostly format?
Yeah, I think this paper probably is one of them, but there are many other papers. So I think this is the example I was trying to show. So just only interpret this point. This point means that you flip the label in the exemplars. So you change the label to be exactly flip the two labels, and you test on the original label. So if you actually learn, then you should have terrible performance because you learned to flip the label. Your performance is terrible, and that's exactly the case. The performance is terrible.
Also, they're not necessarily at odds. It depends on the distribution. If it's like random labels, then the model is probably like more likely to just retrieve the task. But if there's a systematic pattern, it's like
So this you can both learn the format and the real relationship both. Yes, but this is a case where
in parallel and like at some point one signal takes.
I mean, in fact, the points that say 50% flip label is exactly random labels, right?
No. This is not. Yeah, my bad. This is not. When you say flip labels, you don't mean you flip in a consistent way. You have like 5 labels. You flip 3 of them consistently for every exemplar. That's yeah.
Randomly drawn. It's like if it is yes, you will make it no. It's not like an S could be with 50% yes and 50% no. I don't think that 50% here is random.
So then maybe I don't understand what is this example. I thought I.
Oh, I see. So
I interpreted your chart as saying I give a prompt with 100 examples and I flip 50% of them or 25% of them.
I see. No, sorry. I think maybe I'm so because here the labels are when you say flip, it's binary labels. So how do you? Okay. Yeah, my bad. I'm. But at least this one is clear. Let's just only focus on this.
I understand.
Yeah.
100% I understand.
Yeah. Let's just do. I think 50% it probably means random. Yeah, I think probably means random labels. Yeah. 50% I think means random labels. But this is pretty clear, right? Like
that's right. And I'm saying at least even down the gap from 0 to 50 is very small for most models, right? Even the best model, you see a drop from about 90% to 80%.
Yes, that's true. That's true.
So you're still even with random labels, you're succeeding at 80% in the downstream task.
Yeah. So you are using a prior, right? You are using a prior to some degree. In this case, right? You are using a prior information, but in this case, you are not. You override the prior information. You really believe that the one label is the other, right? Yeah.
Got a very naive question. So I was trying context learning on my phone. So Albert Einstein is German. It seems it's very good at that. No. But when I try the three simple two, that one it doesn't get it right.
ChatGPT doesn't get it.
I need to ask you to try again. Well, eventually you get it right. And I was just curious when I ask again, try again, get it wrong again.
But if you try harder, sometimes.
Don't worry. It seems like a
Yeah. This is Oh, so what's your question?
My question is, in your training, do you have to do something like this? Well, how do you, it seems to make it very challenging to do the
I think the only thing is just that these days ChatGPT, especially OpenAI's models, they have a lot of RHF, and they basically don't let you over. And also, they don't have incentive to let you override. So, for example, what if you try to in the context you tell the model to do something bad and evil, right? So basically they want to stay with the prior. In some sense, they don't have a strong incentive for the models to learn because you may teach the models to learn something bad. So I think that's so that's why with the OpenAI model it's very hard to do this. Not very hard, but like you need a little more instructions. You say, please trust me, follow my format, like be a little more persuasive. I think actually I found some. I spent some time digging into some of the newest experiments with in-context learning, and they have to use a little bit longer prompt to make sure that it follows the instruction. But if you use Anthropic, and this is what I heard from Michael, I sent him an email two days ago saying that I couldn't reproduce some of the examples, and he told me that he tried Anthropic and some of the other ones, it still works. So it depends on some of the details whether they have done enough RHF there. All of these are GPT, but some of them are actually not. They are not. I try to be. Yeah. So some of these are GPT for all latest, and some of them is GPT 3.5. I think this is 3.5. So if you try it from different models, it's also the behavior is a little bit different. The plots are. Let's see. This is done by Google when I was at Google. So they only have this is the exact model ID.
Easier to get consistent result using these models than GPT?
I think you can get consistent results with GPT. It's just that you need to try a more complex. These are actually Text DaVinci is GPT. But
Probably not instruction.
No.
Text DaVinci, whether there's Text DaVinci, I think has RHF probably. I think. But in those days, the RHF is not that strong. So, basically for every model, you have to tweak a little bit the instruction so that you can consistently follow the instruction. And for this kind of like early days models, you don't have to do much. You just dump the exemplars, that's fine. And these days, I think you need to have a little bit kind of like instructions on please follow my format, and this is a learning task, something like that. Okay, I'm not sure whether, okay.
Just one last question.
Sure, yeah.
Linear regression is a very simple form of hidden markov models. And have you tried more complex intent synthetic data?
Yeah. We in the paper that we proposed HMM, we had a experimental section where we actually released a data set, and on the data set you can see relatively consistent observations as for GPT-4, GPT-3. So you can see all of these in context learning and so on and so forth.
So I'm asking this because in practice, GPT, some people are suspicious of its in context learning ability, just as what he just said that he will ChatGPT will flip its answer if you ask, "Are you sure?" In synthetic data, it would be clear to see if it can really learn HMM.
Yeah. But we have tried that. It does work, but it's not that surprising because the theory says it should work to some degree. The only difference is what I said. You have the reset. So.
What assumptions do you have on HMM?
Nothing much. Just empirically we just construct some HMM with like maybe 10 states or something like that.
Okay, well, thank you. And we take the part outside if there is